This is HeeRyang Choi from SQRT, and today I'm going to talk about supremacy with complexity argues. Okay. Okay. So before I start, let me announce to you about this all about things are based on review paper of Jens Eisert and Dominic Hengleiter. You can find it in the uh, review papers of the modern physics. Okay. All about the supremacy things. Uh, our every argument always start with the definition of the Turing machine. Well, the former definition of the Turing machine is so a little bit complicated, as you can see, but the most important thing you have to know in this sentence is a Turing machine is defined by the deterministic transition function, which means that if you are in a one state, then you will go to the another state with a deterministic way. So which means that there are only one way to inputs to outputs. Every ways are deterministic, and there are no changes between there are no changes if we do not change the Turing machine's encoding. But sometimes this definition can be varied by we choose this deterministic transition function into a non-deterministic transition function or quantumic or probabilistic functions. So we are going to start here. By this definition of the Turing machine, at the early 20th centuries, Church demonstrates his hypothesis as Church-Turing hypothesis by every function which would naturally be regarded as computable can be computed by a universal Turing machine, which universal Turing machine is described as before. But maybe this is a little bit unprecisely to some people because naturally be regarded as computable is not very formal, mathematically formal definition. So at 1985, Deutsch, who are the early inventor of the quantum computers architecture, suggest some kinds of new type of Church-Turing hypothesis as like this. Yeah, every finitely realizable physical system can be perfectly simulated by a universal model computing machine operating by finite means. In this type of definition, in this type of hypothesis, we can Deutsch says that classical computer, which means that classical physical systems cannot demonstrate the universal Turing system because of the uncertainty principles. Classical computers cannot always have cannot always demonstrate kinds of Turing machine, which means that every inputs and every states will reproduce every same outputs as definitions. So Deutsch describes some kinds of new Turing machines or new kinds of computers will be needed to satisfy this kind of new Church-Turing hypothesis as mathematically formal. Yeah. So the early development of quantum architecture is started from the Feynman and Albert and Deutsch. To satisfy these kinds of new Church-Turing hypothesis. And then if Deutsches nuke type of the quantum architecture, which means which called as a universal quantum computer, which is modernly used architecture of the quantum Turing machine. We can have a new type of questions about what kinds of things we can do with this type of universal quantum computer. So then Verghese suggested some kinds of strong extended type of church Turing tests to despite that the analog computer, which means the quantum computer, is more stronger than we think before, as like these statements that any finite analog computer can be simulated efficiently by a digital computer in the sense that the time required by the digital computer simulate the analog computer is bounded by a polynomial function of the resources used the analog computer, which means that if there are enough time and satisfiable algorithms, then any kinds of computers, in analog computers, which includes quantum computers, can be simulated efficiently by digital computer, as we know, what we used in these days. Yeah. But some people think that this is not true. So as pre-skill at 2021, he thinks that extended Turing tests can be violated by some kinds of quantum machines and quantum algorithms. So he called it as a quantum supremacy or advantage if we find an experimental evidence of violation of tests. And if we wanna talk about this experimental evidence of the violation, we have to satisfy the conditions with that evidence about independency of the specific algorithms and the intrinsic complexity conditions. Yeah. It is because there are many problems that can be solved easier by quantum computers than classical computers. As we know, the Grover's algorithm, search algorithm, or factoring and Loloid simulators and other various developments. But in theoretically, this is based on the Feynman vector of the universal quantum computer. If we think about that, some kinds of quantum device can be efficiently simulate parallel processing than digital computer more faster, then it is a direct violation of the extended church string thesis. But as you can see, if we define the left front type of the state and some kinds of quantum device machines to make the third qubit as an Fi, if there are non-trivial n-fold parallelizable function large GF isn't exist, then we can demonstrate this I, comma Fi as into the large GF term and the lambda F term, as lambda F term has no information about the parallelizable function, and the GF is a parallelizable function, and with the portion of the beta, then by another function g, which is an equivalent to it, f but not identical, we can inner product them to get the third equation. And here, we can see that if large GF is not a constant function for each function, and if we interpolate small g and small f as an same function for every i's, and also not same for large g's, then we can get that 1 minus large n over 1 is equal with that term, and this means that beta is smaller than square root over 1, so which means that the quantum device cannot be used to improve the average mean running time of the parallelizable programs. So with these kinds of arguments, we can think about the Bell's inequality maybe extended Church-Turing thesis is some kinds of computational analog of the Bell's inequality. Then, as we know, Bell's inequality is wrong. We can prove it by experimental evidence. Then we want to talk about what's a computational analog of Bell's inequality as a means to test localisms. Which means that we want to find it to achieve supremacy, but maybe this is currently not precisely understood. Maybe some kinds of candidates are exponentially growing Hilbert space size or entanglement or quantum interference, like that. So if we want to achieve quantum supremacy, then we have to achieve some important conditions as firstly, it can be performed on NISQ devices because we are only in NISQ area, which means that noisy and on intermediate scale quantum computers. And also, it must be computationally difficult to simulate for classical computers, both asymptotically and practically, because practically it is natural, and because of the mathematically formal purpose for mathematically formal explanation, we want to know about asymptotically difficult. And also, we have to know about it is really good that task has been really successfully run, which means that we need some kinds of available benchmarking methods. So with these kinds of preliminaries, many people think that random quantum sampling circuit can be key concepts for supremacy, which means that it can satisfy these 3 types of conditions to achieve supremacy. Then we have to know about what really sampling problem is. Sampling problem is a natural class of problems for quantum device and sampling problems, quantum device, because for every quantum devices, every quantum problems, there are experimental prescriptions and repeated measurements and intrinsically random measurement outcomes, and therefore probability distribution by the Born rule. And this is exactly the definition of the sampling problem. So some people think that sampling problem itself, because it is the natural class of the quantum devices, quantum simulators. So the sampling itself would be challenging for classical device because of its features. I'll say it later. Informal definition of for the description of the formal definition of the sampling, we have to know about desired probability distribution, and also we need sampling machine to do sampling, which means that desired probability distribution is an target distribution for the for the for the outcomes that which we want to simulate it, and the sampling machine is use this desired probability distribution to get random instances of the sampling, which means that in the other words, this QU, if this QU is this if no Hmm. Hmm. Ah, let me skip it here. Then if the if sampling problem is just as an get some random bit strings from the desired probability distributions and corresponding probabilities, then we can naturally think that why sampling problem is sometimes hard, because we can uh we can use mathematical tools to demonstrate the target probability distributions, and well, sampling machines can be just made it by some tools, Python, C. Then why relay sampling is hard? Because it is to perform sampling, the machines which out some bit string and corresponded probabilities, machines must be run in each time of the sampling process. So if we want to sample a lot of samples or a lot of instances, then we have to perform the sampling machine as a lot of times. But well, sometimes machine has high time complexity, because sometimes they demonstrate the probability distribution is not very easy, which in the other words that probability distribution cannot be easily demonstrated by basic mathematical tools, not always. And sometimes we have to attract it very, very complex ways. Informally, we can say about this three levels of the definition. At first, we calculate the output distribution and using it as an oracle. Which oracle means that sometimes of God's message, which means that no complexity, which means that we don't know how, but it works. And at the second level, combine this oracle with a simple type of random bit string generator. Simple random bit string generator means that just some types of classical random number generator, which runs with very fast time, and we combine this probability distribution oracle and the random number generator. We can make some kinds of machines to make complex sampling problem into the simple definition. And so therefore the sampling problems looks like tractable one. the right images shows formal definition of this description. But the hard point is deconstructing the oracle is sometimes very hard, as I said before. So, yeah. So the random quantum computation, which means that random quantum circuit computations, are some types of problem that very hard to calculate the output probability distributions. Even if it's just a toy model that means nothing and not valuable. But there are some usable features that there are two types of randomness that we can randomly choose circuit instances in the architecture based on the classical random generator and the randomness of the output state, which is based on the Born rule, which is a physically natural way. And also, we can choose various models as universal circuit sampling, boson sampling, IQP sampling, and that various models. With these kinds of good features, quantum random sampling is defined as like this. Yeah, we can choose with sample size, which means the qubit size, and we can define the circuit family Cn and sample the output distribution of the circuit as Pc with the sample space omega. Then we can demonstrate the Pc as the types of bracket notations by samples outcome S. And this is the definition of the random quantum sampling, because we have to choose an output as a random, and also the circuit instances as a random. Universal circuit sampling is more precise definition of the random quantum sampling, which is that every gates construction circuit are drawn from a universal gate set, which that universality means that these kinds of gate set can consist every type of unitary transformations, so can demonstrate every type of circuits. This feature is very important for supremacy because it means that just a programmable, it just a programmable computer can be made it. And also for the complexity proof. And these gates are placed at certain positions in a circuit architecture. Might be fixed or random. Randomly positioned gates makes more randomness, but might be fixed to fixed is enough. And also it can contain some kinds of non-random gates. X gate or Y gate, some Pauli gates. Yeah. Good example of this universal circuit sampling is in Google's experiments at 2091. Firstly, demonstrate the quantum supremacy by a real quantum device. This is Google's architecture. At first, there are some 1-qubit gates. These are randomly drawn from the set W and X and Y, which W is just X plus Y and average it. So the X, Y, and W are just single qubit rotations. And there are fixed type of the 2-qubit gates. You can see it in the right top I swap gate, which called as an FSIM gate. These 2-qubit gates are fixed and always the same, but these gates are these gates are distributed in architecture by the gate pattern. You can see it in the below, A, B, C, D, C, D, A, B, by some kinds of pattern that makes circuit pseudo randomly, because the pattern is fixed, so not very random, but seems very random. Yeah, this is it. And with this kinds of architecture, it is very 놀랍다가 영어로 뭐더라? Yeah, so it is very surprised because these types of non-randomness, because there are only 1-qubit gate randomness and the other things are all be fixed, we can see enough level of randomness to achieve quantum supremacy and sampling hardness. Yeah, it is very surprising moment. Yeah. So this is definition of computational universality. I've said before. And yeah, Google's experiments consist of root square X, square Y, and square W, and FSIM gates. And these types of gate cells are universal and have a universality, which means that every types of unitary and every types of operations can be consisted by the architecture of Google's circuit. This is based on the three level of proofs. Firstly by Boykin, and after DiVincenzo and by Google itself. And why we need universality to say about quantum complexity. It's just because programmability for the entire Hilbert space operations, which means that ability to simulate, are very important to achieve complexity hardness. Because as Clifford gates, we know by Gottman theorem, some gates can be efficiently simulated by classical computer. So we have to verify that our computer has enough ability to simulate average cases. And also, universality of gates sometimes plays an important role in the proof, which means that universality is a good tool to mathematically show that some types of quantum problems can be classically intractable or very hard. So yeah, now we were going to talk about how exactly complexity hardness is proved for these universal random circuits. And first, we know that some complexity groups P and NP, which is well known by the assumption conjecture P is not NP. It's just easily defined by the P is a deterministic and the NP is a non-deterministic operation. In the other words, or easier, P is a types of problems that polynomially tractable by deterministic computer, which means that one state to next state to output state is always deterministically moved. So if start is fixed, then the accept or reject output is also fixed. But the non-deterministic computations is sometimes more not sometimes non-deterministic computer can be different, which means that if we start with one state, then we can vary into a lot of states by computer itself, and then varied states can be also varied to many states to compute to find the reject or accept to find there are accept ways or reject ways in the halting point, which means that finishing point of that state. So it means that as quantum computer, non-deterministic computer can explore the every space of that problem at one running process, which is different that because deterministic computer cannot explore the entire space at once and just have to run many times. Yeah, it is difference between the P and NP. So intrinsically, that we may think that NP computer is much better than P computer. But yeah, it is not proved yet that P is not equal to the NP. But it is also generally believed because if this conjecture is false, your money will be gone. Much of the modern cryptography would collapse. So we will use this conjecture into the proof of the hardness of quantum universal quantum circuit sampling. Okay. So if we want to know about quantum computer is better than classical computer, then we have to know how exactly classical computer can do. What classical computer can do, what classical computer exactly can do. Yeah. So this is definition of the random classical circuits acceptance probability calculation. Well, this is formal definition, but we don't have to know it. We don't have to know about it specifically, and just say that this is Sharpe problem, which is that classical acceptance probability calculation is just a Sharpe problem, which is a Sharpe problem is counting the number of accepting inputs, which means that if as we said before, P computer is deterministic computer with follows just a one way, and non-deterministic computer is non-deterministic process to explore the entire space at once, then sharp P problem can be similar as NP. Maybe at the NP computer, some directions are ended with reject results, and some directions can be ended in accept results. So there are numbers, so we can count that what number of directions are ended halting with reject, and what number of directions are halting with the accept result. Then sharp P problem is just simply defined as calculating what is the number of accepting directions. This is why sharp P problem is corresponded to the classical acceptance probability calculations, which means that classical random circuit acceptance probability calculation is just directly an analog of the random circuit. Yeah, as simply you can think that light non-deterministic tree as an random classical circuit, and finding the acceptance probabilities are just follow them down and the checked what directions are accept and what directions are reject. Maybe we don't have to think about reject. So it is because it is the reason that why sharp P problem is an complexity class of the classical random circuits. And there are another complexity class as called gap P, which is derived from sharp P class, is calculating the difference between the accepting and the rejecting directions, which means that there are reject and accept directions. Then we can know that number of the accept directions in the sharp P problem, and for sharp P problem, and that is it, and it is. But for gap P problem, we can also calculate the number of reject directions and calculate the bit difference between them. But in generally, we can know that in what is exactly the entire space of the problem. So generally, sharp P is equivalent with gap P under Cook reductions, which means oracle reductions. And why I explained about gap P is because quantum acceptance probabilities are gap P problem. It can be derived as this simple calculations. Well, we can think that calculation of the quantum acceptance probabilities of random circuit can be derived as this equation 17 with a circuit Cn and some input x. If we want to know about what is probability of Cnx is accepted, is we can just calculate it by bracket notations by y Cnx and square for the every accepting outcomes y. Yeah, this is very natural definitions. But sometimes without loss of generality, we can say that we can fix the y as 0 it calls sometimes hiding property, because it is just because as at the architecture of the random quantum circuit, you can think that for some y, which means that accepting outcome bit string, how about we just place some Hadamard gates into the first row or the last row of the circuits? Then maybe we can no, not only Hadamard gates, with X gates or some Pauli gates. Then maybe we can think that just every instance of y, even if it is randomly chosen, we cannot distinguish the difference between the two bit strings, two bit strings, because if we place some Hadamard and Pauli gates patterns into the start or the end of the circuit, then the outcome bit strings can be mixed, which means that every y has the same portion of the every y has just same portion of the weight of at the output distributions. Yeah, I maybe this expression is not good, but yeah. So yeah, indeed, we can just fix y as 0 and skip the summation process. With this, quantum acceptance probability of random circuits can be simply expressed as this. And also, we define function gx as this, as you see, that yeah, maybe this definition might be needed some derivations, but yeah, it is in Adam Harrow's paper in the 17th. Yeah, you can change the above definition into the below definition by some basic calculations with Feynman path integrals. Feynman paths. Yeah. And it'll be gap P problem. Yeah, I'm sorry for not explaining these detailed descriptions. Yeah. So we now know that classical simulation is sharp P problem and the quantum simulation is gap P problem. But maybe if sharp P is equivalent with the gap P, then there are no benefits to use quantum computer or in contrast that maybe maybe classical computer is so bad than we think. But in approximating case of sharp P and gap P, maybe the results can be varied, which means that approximating gap P function is into the multiplicative error is still gap P, but approximating the sharp P problem may be easier than gap P, which means that sometimes the classical random circuits can be easily simulated by computers. that argues are based on the Stockmeyer's algorithm, which is NP Oracle algorithm. NP Oracle means that there are a set of some kinds of NP problem solvers with zero time. This algorithm is a kinds of algorithm that makes sampling problems into the deterministic problem, which means that random problems into the deterministic problems with multiplicative errors. So it's just types of heuristic. Yeah, then by using it, this is the definition of the Sharpie by counting the acceptance ways of the problem. We can approximate this within FBPP over NP, where FBPP is some kinds of complex C classes. B is relative to the P class, but much bigger than. So by Stockmeyer's algorithm, approximating Sharpie problem is FBPP and is FBPP with NP Oracle. But when Rautmann at 1983, he proved that BPP is contained in sigma 2, which sigma 2 is defined as right figure as NP with NP Oracle. So the BPP with NP Oracle is also contained in sigma 3, NP Oracle, NP with NP Oracle. Yeah. And also, at 1991, by Toda, he proved that infinite oracle separations of the NPs, which is which code as a polynomial hierarchy, as defined as right figure, is included and as Sharpie problem, where the Sharpie problem is just said before that random classical circuit sampling problem is Sharpie, and also the random quantum circuit sampling problem is GAP-P, and they are equivalent. So we can therefore we can say that as the last inequality, approximation of the Sharpie with multiplicative error can be contained in the sigma 3 class, and this will be not equivalent and be included in polynomial hierarchy class if P and not P and NP is not equal. And also, by Tora, this is included in this polynomial hierarchy can be included in the Sharpie class, and the Sharpie class in equivalent with GAP class. And also, by Hang-Glider, approximation of GAP-P is equivalent with GAP-P with some conditions. So we can conclude that approximation of Sharpie, which means that approximation of the classical random circuit sampling problem, is much easier than approximation of the GAP-P problem, which is a quantum circuit sampling problem. Then maybe we can think that it is a supremacy because quantum circuit sampling is more harder than classical sampling circuit. But we have to know that this is just this process is just doing on that in just a multiplicative error era. But yeah, but sometimes in real world, errors cannot be multiplicative and be additive because as we know, in quantum computers, some exponentially large probabilities have just exponentially small portion, and in contrast, exponentially small probabilities has exponentially large portion, which means that if we assume the multiplicative error, then just for the small probabilities, it can be precise, but for the large probabilities, it cannot be precise because the error is relative into the size of the probabilities. It is not yeah, in real quantum devices, it it is it may be not because yeah, various quantum devices just as an error as an additive, not relative, but an absolute error. Yeah. So yeah, time is over, but there are some kinds of yeah. If we want to know about quantum supremacy with complexity, then we have to discuss about additive error and yeah, some more complex argues. Yeah. If we want to know about additive error, we have to define some kinds of new distribution, new measures between two distribution probabilities as this total variance distance, just summing up the probability distribution differences and average it. Yeah, I know, half it. Yeah, there are many proofs that these kinds of total variance distance, which is an additive type, is very natural way to write error for noisy devices, as you can see by some by positive measures, and the trace distance by using it, then total variance distance can be bounded by the relative bounded by the portion of the state error in the target state and the noisy states. Yeah. So sampling task with additive error might be different with the multiplicative error case. Yeah. For the additive error, we can define the target of the problem, which object claim of the problem as this p minus q. Total variance distance between p and q is have to be smaller than epsilon. So by definitions, when the epsilon goes to 1, then we can use just q, which pc is in the ideal distribution and the q is our distribution, approximate distribution. Then when epsilon is 1, then we can just use q as uniform distribution, then it can be satisfied. So yeah, if epsilon is bigger and bigger, goes bigger, then problem becomes more tractable. But by the last Cuevas paper at the 2011, there are known bounds for the gap p-hard limit, which is that by the number of the qubit n, epsilon must be smaller than exponential of the n, exponentially small with the qubit numbers. Yeah. because we need to prove it with case of arbitrarily de-randomizable algorithms where the randomizable algorithms are defined in here. Sampling, formal definition of the sampling problem. So the exponentially small additive error can be this exponentially additive error, small additive error can be regarded as a total error budget in our proof sketch. So we have to combine our process errors into this budget. This is our 9 of the proof. Yeah. At the C, it's the circuit architecture, which is given. And the central machine is a sampling machine, as I said before, with the target distribution PC and P, which is a given distribution for the sampling machine. With the sampling machine, we can choose 2 types of way to go to the object, destination. At first way is just use Stock-Myers algorithm to approximate it. It's the right way. If we use Stock-Myers algorithm to go here, then with complexity of NP oracle with FBPP, we can make Q0 approximated output with Stock-Myers algorithm with multiplicative error, because it has Stock-Myers algorithm has multiplicative error. Also, by sampling machine itself also produces some kinds of output probabilities because it is machine. And it will be have 2 errors. That one is additive error between the ideal distribution and the destination distribution, and total variance distance, which is defined as before. Yeah. So we have to deal with these 3 types of errors. To prove supremacy, we have to show that the sum of multiplicative error and the additive error is have to be smaller than TVD error between ideal distribution and the sampling distribution. Yeah. To achieve this, we can use some types of adversarial approach. At the multiplicative error case, we can obtain that approximation Q0 and the noisy output P0, it can be just expressed as error constancy with error constancy, as like that. Then our goal can be simple can be expressed as simple as the second inequality in the slide, where the P0 is the ideal distribution and the P0 is output distribution and the Q0 is our approximation, which is that P0 is ideal and P0C is ideal, and the P0 is an output of sampling machine, and the Q0 is our approximation by Stock-Myers algorithm. So we have to bound the error between the Stock-Myers algorithm and the ideal distribution with the the absolute inequality. And also that because this absolute inequality satisfied, so if we use very specific de-randomizable algorithm to maximize the second term in the right hand side, maximize this additive error term, then the bound of the error can be maximized, because and it is very, it sounds like very non-natural, but it is natural, because we approach with very adversarial way with the definition of this central sampling machines consisting. Yeah. And in picture, which we will approach with adversarial ways with the maximize that that distance between the two distributions by just setting our sampling machine and modifying our sampling machine's algorithm very maliciously to make that sampling machine's output and the ideal distribution are very far away, placed at a very far distance, even if it is not sounds natural. Then it works with no contradictions. So we can say that for certain cases, we can know that there are clear evidence of supremacy, or just certain cases, because that our adversarial attacks has no contradictions. Yeah. In cryptography, we sometimes call it as a worst case, but it means nothing in reality, because to guarantee the supremacy in the real world, the complexity arguments must be ensured for a large fraction of the instances, not on small and certain parts of the instances. And this is well known as a cryptographic term, average case hardness. But unfortunately, currently it is not have been proved, which means that there are no clear evidence for supremacy now. So there are many recent works for the attempts to bridging this gap between the worst case and the average case real supremacy. It is based on the just worst case to average case reductions. This can be maybe a good picture to demonstrate the reduction. The left side is the worst case, and the right side is the average case. And there are some kinds of interpolation paths between the worst case and the average case, targeted with a control the error bound. We can achieve worst case to average case reduction with some kinds of robustnesses. But robustness means that for one worst case, then some portion of the average case can be obtained by this path. Then if we have one worst case, then only one, if the path path or series are exact, then we can just obtain one, instances for the average case. So this may be not good. So robustness must be more bigger to achieve quantum supreme achieve uh desired scale, because as the desired scale of the robustness is an exponentially small with n with big O notation. It is because by with the 2 over with the scale, we can generally say that there are no difference between the randomly select 1-bit string or just tractably simulate something. Yeah, maybe this can be sound complex. Yeah. Just you can think this as an desired robustness have to achieve some kinds of saturation limit to makes every state equivalent. Yeah, there are many remaining topics, but yeah, I over time. So yeah, let me finish it. Thank you for listening, and sorry for my bad English. And if you have any questions, feel free to ask me. Thank you.